If you have any questions, please feel free to type your questions in the chat window, and those questions will be answered by the speaker at the session.
So first of all, thank you all the organizers from the IEEE CS chapter Bangalore for inviting me for this talk, for this nice event, even amidst the dark pandemic times all around us. I hope all of you are keeping safe and protected. I hope my screen is now visible to all of you. I'm going to make it full screen. And at any point of time, since the internet connections are always unstable, so if there is some issue with viewing my slides or you cannot hear me, please immediately let me know. I'll try to reconnect or do something like that. So although the title of this talk is a little bit heavy, the class imbalanced machine learning, the word machine learning is not very unfamiliar to us these days, not at all actually. This particular phrase has entered into our drawing rooms, into our tea tables, everywhere, all around us. And practically, the theoretically very sound systems may even very often fail, especially when the data on which all the machine learning algorithms, pattern recognition, data science algorithms feed, when the data comes with a lot of discrepancies and irregularities, one of which is this class imbalance problem, then the machine learning systems have to be adopted through some extra auxiliary techniques. This will be the focus of this talk. Obviously, there is some research, recent research trends I will discuss, and I will also highlight most promising directions in this particular area, apart from highlighting some of our works in this particular domain. This is the first slide, and in this first slide, the most important data, obviously machine learning people have to understand which particular data item is significantly important. The most important data is my email ID. If you wish to ask any even offline questions, or if you require any reference, do not hesitate to drop me a line. I will try to revert back. Okay. And I start with assuming a zero background knowledge. So because some of the audience may not have sufficient, expertise. I understand it's going to be a mixed audience. Some of you are great experts. Some of you may not have that expertise in this particular area. So I start with a zero knowledge and at the concept level try to develop the things from scratch. So what is machine learning? As we all know, there are two words, machine and learning. If we set aside all the philosophical aspect, a learning system is a system which can take a future decision based on past experiences, and with more and more experience pouring in, the capability of taking this future decision increases. When I was a kid of 4 or 5 years, or all of us have gone through this experience, my mother used to point to a kid's storybook and say, look, this is a cat, look, this is a dog, look, this is something else. After a few rounds of such training, on one day when I go on road with my mother and a little creature passes by me, I would yell out, "Mother, look, that's a dog." I'm very excited. So what did I do? Based on the experience provided to me by my mother, I took a decision about that creature which just passed by me, actually. Although that dog which passed by me on road was not the exact one printed in that children picture book, but somehow in my mind, I could interpolate the gross appearance, texture, color, etc. of that creature was stored in my actual neural circuit under the tag word of dog, and I could match it, right? And with more and more experience, this decision-making capability also increases. This is human learning, it's not machine learning. Machine learning also, apart from learning, the word machine is there. And machine means, up to now, we haven't have experience with quantum computers practically. So till now, machine means a stored program concept enabled classical computer with von Neumann architecture, which could be described in terms of Turing machines of different phrase and so on. So the problem of machine learning is how to inculcate such human form of learning with which we are habituated since our early childhood into a computer. That's the central question. And here is a difference from traditional programming. In traditional computer, we provide some data and we just provide a program. What is a program? It's a stepwise set of instructions executing which the computer will generate the desired output. In case of machine learning, we provide some data to the computer and we also provide some expected outcome from the data. For example, we can provide the computer with some unsorted lists of integers, and we can also provide the computer with the corresponding sorted lists of integers alongside some constraints also, like you need to sort it in least amount of time by occupying least amount of memory space and so on. And the dream of machine learning is let the computer learn how to sort. Let us not write a sorting algorithm for it. Let it write the algorithm itself. Let it write the program itself, which is a translated version of the algorithm. Let it discover a new merge sorting algorithm, or maybe an equivalent to merge sort, hit sort, any other quick sort, anything like that. That is the dream of machine learning. And there are three types inside it. We will today, in the rest of the talk, I will mostly focus on the supervised learning aspect. So there are three different aspects. One is supervised learning, where there is a direct teacher involved. There is a human expert whose expertise will be somehow translated into the machine and let the machine, based on those expertise from the human user, let the machine start taking its decisions. One very easy example is let us hire a doctor and let us have the breast tissue mammograms from different patients. In these breast tissue mammograms, if there are off-white spots, which are very difficult to recognize unless you have a very experienced eye. So in the background, the white background of the tissue cells, these off-white spots indicate the onset of breast cancer. Breast cancer, if not diagnosed very early, at very early stage, it can lead to very bad consequences. So the doctor is hired. Doctor is an oncologist. His time is extremely valuable. The doctor manually labels such initial 100 or 150 breast mammogram images, breast X-ray based mammogram images into two classes. Some images are perfect, no trace of such off-white spot. These are benign. In some images, such traces are there. These are initially diagnosed as malignant or early malignant. But the doctor is extremely costly. He will have time only for 100, 150 images. Now, these manually stamped images will be fed into a machine learning algorithm. The algorithm will be developed in such a way that when an previously unseen, unexperienced patient comes and his mammogram is there, the computer will scan this mammogram and take a decision on whether the patient should return back home or whether the patient requires immediate medical attention. That means whether the patient is benign or malignant. So somehow the doctor's expertise should translate into the machine, just like as my mother was pointing to those pictures and saying, look, this is a cat, look, this is a dog. This is the same way. So we call it a supervised learning, and the supervisor is like a teacher who is like this doctor, or who is actually a human expert whose expertise must translate. Then we have unsupervised learning, under which it is important to discover the naturally occurring groups inside the data, and based on certain dissimilarity or similarity measure among the data points. And in case of unsupervised learning, nothing else, no external labeling is there. No external set of examples with human expert-based labeling is provided. And then we have a midway between these two, which is called reinforcement learning, where there is a learning agent, like a robot, which has to move from one corner of the room to another corner of the room. And this learning agent interacts with the environment alongside it or around it. Based on such interaction, the learning agent either receives some reward or receives some penalty, and it plans its future course of action in a way to maximize a discounted sum of such rewards. There are some mathematics inside it, but it is somewhat midway between supervised and unsupervised. It's like learning from mistakes. There is no active teacher, but there is an environment to provide feedback on each of your action. Obviously, you perform some action on your environment and you will receive some reaction. Reinforcement learning is about judging such reactions and planning the future actions accordingly. We can summarize the whole business of machine learning, especially supervised learning, with a very simple mathematical equation, that is y equal to f of x. And what is so speech, and how does that map to the recent application? Speech recognition. We have Alexa from Amazon, we have Siri from Apple, and many other speech-based assistants, Google Assistant. Okay, so you talk something, you talk search for COVID-19 vaccine availability around my area, and automatically you don't have to type. Google will search it and show you all the results because it has a speech interface. Okay, so which is basically your speech is going inside the function as its input variable, and the inside the system the function returns the transcript, what is there inside the speech that is returned. Similarly, image recognition, the image goes inside the function x and the function returns the correct label for the image. Playing a game, it can be an image of the game board and the function may tell you what move to be taken next. Okay, predict the next move. Dialogue system, which is used by chatbots these days. So you type hi and the system automatically responds hello, although no human user is sitting on other side. So the basic framework is you have a set of functions. Different functions make different machine learning algorithms, and different functions will provide you different responses in exchange of the input. And these functions are called model. The models are inside the actual algorithm or meta algorithm. The training data comes with human labeled images, just like the doctor was labeling whether it's cancer or benign. And this training data is used to judge the goodness of a function at your repository. The machine learning algorithm actually defines these functions and finally gives you the best model or the best function. This is supervised learning, in fact. So pick the best function F star and use F star for previously unseen images, for taking a decision about the category of previously unseen images. So as you can see, these externally labeled set of examples are called training data. And then when a new unseen example comes and the machine has to infer what it is, cat, dog, hippopotamus, this new unseen image is called the test example or the test data. Okay, so these are the very basic steps of any supervised learning system. But why it is so hard? Before I go into the actual theme, this is just a prelude, so I'm hurrying a little bit. So why it is so hard? Because human beings are very good at recognition, perception. Human beings are gifted with 5 sensory organs. Machines don't have it, okay? And human beings are gifted with the visual cortex, which is one of the most intricate and most high-level engineered object in the entire universe, or engineered probably by the Almighty. Okay, so when you look into this picture, you immediately realize there are wheels, handles, etc., and you call it a motorcycle. But what does the camera see? The camera sees piles of numbers. These numbers are the the gray level intensity or color code, pixel value, etc., inside the particular image. So you see the such images inside, such numbers, piles of numbers, and it is very difficult to infer something from such piles of numbers, okay, by the machine. If we represent an image in terms of only 2 pixels, plot pixel 1 along x-axis, pixel 2 along y-axis, and each image becomes a point in this 2-dimensional space, you mount a camera on the doorway of your garage. You don't want an elephant to walk into your garage, or a cat or a dog. So you want to distinguish between cars versus non-cars from the images captured by your camera. But what will happen if you just take 2 such pixels, completely uncorrelated, meaningless and plot them along x-axis and y-axis. That means you are representing each image as a point in this two-dimensional space. What will happen? Cars and non-car images will become a khichdi, a complete mixture. You cannot actually, separate them out. On the other hand, every data item, be it an image, be it a text document, be it something else, every data item must be abstractly represented to the computer in the form of a group of numbers sitting together and specifying that data item. These numbers are called features. Better feature representation is the first key step towards doing good machine learning or towards good recognition. And features vary from context to context. So when our objective is to demarcate between cars versus non-cars, we can take 2 3x3 or 5x5 windows and drag these windows over the image. These windows are fitted with cleverly selected coefficients or learned coefficients, such that when such a window captures a handle-like shape or a wheel-like shape, it registers a very high number. Otherwise, it gives a very low number. Its output is a single scalar number, which could be very high if within the window there is a handle or there is a wheel-like shape. These are called feature detectors, and these are the key techniques inside a convolutional neural networks used nowadays hugely for image classification. So we can record the response of the handle and the wheel detector along the two axes, and then the cars will accumulate lot away from the origin, and the non-cars will accumulate very near to the origin because they have very low response along both the axes. So better feature representation. Each of us are one data item. When I go to a bank, I become a data item. You become a data item. You are a customer to the bank, and you are specified by a number of fields put together. Okay, number of attributes or features put together that may contain ASCII character-based name, street address, but also numerical items like your account balance and other things. Okay, but when you apply for a loan, then the bank will see how much interest you paid, whether you have a house, whether you have a good job, etc. But when you go to a blood bank and when you try to donate blood, in that case, to the blood bank, you are also a data item, you are a donor. But the blood bank will look at completely different features, whether you have high blood sugar, whether you have high blood pressure, do you have any family history of any other diseases, etc., etc. So based on the context, the features can abruptly change. Context-aware feature engineering is one of the key steps towards it, and human beings are very, very good at it. So if you look into these 16 images in 2 categories, you can immediately say which one is a sheepdog or which one is a mop. If you look into these images, you can immediately say which one is a puppy or which one is a bagel. You don't have to do machine learning. But if I want to make a computer, this is one of the very tough data sets for a deep learning system, to which I will come later. So when a computer looks at it, then it requires lots of programs and other things. Not only that, you say what is what, but you can also say you can also point out the features based on which you make such distinction. For example, in this case, what are the abstract, by the way, we do not look at images in terms of pixels. We do not say, okay, the top left corner 236, beside that 152. No, we immediately capture abstract and high level features from the images, and you can tell me based on which features you demarcate them, these images, which one is an owl and which one is an apple, probably by the distance between the eyes of the owl and by the distance between the seeds of the apple. Apple seeds are very close, owl eyes are quite separated. Similarly, Chihuahua or muffin. Here also you can see for the dog puppy, the 2 eyes and the nose, they form almost the vertices of a regular triangle. But the cherries on the muffin, they are not so regularly arranged. So human beings are very, 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 very good at it. And a lot of it, therefore, depends on proper representation of the data items that I want to put in right categories or right racks. So there comes deep learning. The previous 25 to 30 years of history in computer vision, in speech industry, in text mining, in natural language processing have gone into the human intervened feature engineering, which means how to represent a text document, a speech signal, or an image, or a video in terms of the most suitable numbers, in terms of such high-level features summarized in these numbers that can immediately capture the most important traits or characteristics of each of these items and categorize them. But obviously, the human intervened feature engineering, which gave rise to techniques like SIFT, scale invariant feature transform, or Gabor filter coefficients, or text on RIFT type of features in computer vision, they are not universally good. And some images for which SIFT would be very good, some images, some other technique will be very good. Deep learning, the biggest selling point of deep learning techniques, because this will also come in my talk. I will talk about the effect of imbalance in deep era, the era of deep learning. Deep neural networks, their biggest selling point is that they get us rid of this human intervened feature engineering. At least they claim so. So the deep learning systems are, feed forward, or there may be feedback also, but this is a long chain of layers of simple processing nodes, each of which have limited mathematical ability, and the basic features flow through this network in like signals, and while such flow, these features get amplified or attenuated and combined in linear nonlinear fashion to give rise to the context-specific high-level abstract features. And thereafter comes the classification. So the responsibility of representing each object optimally and thereafter classifying it, both are shouldered by this network. There is no need for a human feature extractor or human being to decide how most optimally I should represent this text document or this speech signal or something else. That's the selling point of deep learning. Now we are gradually entering into what I wanted to say. The machine learning field is developing at almost at a dramatic rate. Since 2012, the deep learning era almost started like anything, and the giant software-based companies, including Microsoft, Amazon, Samsung, Hewlett-Packard, Adobe, every such company, Google, Facebook, so all of them started investing huge amount of money behind machine learning. But most of the machine learning algorithms so far we have, including the deep learning ones, assume the data to behave very gently. That's why gentleman data. What is meant by gentleman data? All the classes are equally represented. All the subclasses within a class. When I'm telling you apple, images of apples. Now inside apple, we can have green apples. We can have red apples. We can have yellow apples, different types of apples. When I say mango, now it's the season of mangoes, So many different types of inside that particular class up there. We assume that all the subconcepts are like the within class clusters, okay, groups. So we assume that all the subconcepts within a given class are equally represented. They are all having some examples in the training set. We assume all the classes have equal number of examples in the training set. All the classes have similar class conditional distributions. This is one of the biggest assumptions which prove futile in real life data. We assume, okay, we will have 2-3 classes. These classes, the data inside these classes will come from similar Gaussians. All are Gaussian. Or they're Gaussian, that is a mixture of Gaussians with different, variances and means. But practically, it may come from a completely different probability distribution, which cannot be modeled in a parametric way. Parametric way distributions are like Poisson, Cauchy, Laplace, Gaussian, etc., which you can, there are some predefined, prototype based on which you can model, but the class conditional distribution may be completely something different. We assume that all the features are defined for all the members of the data set. All the features are actually, all members of the data set have all these features. This is valid for very simple data sets, like iris flower data set. All of you know, every flower has a petal length, a sepal width, and sepal width. So we can convert every flower in a vector of 4 numbers as a vector of 4 numbers containing these items. But if we are talking about protein sequences of different lengths, and they are made of 4 particular adenine, guanine, thymine, cytosine, ATCG, but the lengths are different. So one can be ATTCGGGGA, the other one could be CGAAT, and completely different. So these two, if you assume that they have to be represented as a vector of same length, you cannot do that. Also, it can so happen that all the features are not recorded or known for all the data instances. So these 5 assumptions of gentleman data are very often violated in real life. Life is hardly so easy. And when they are violated, so we made a taxonomy of such data irregularities in our 2019, it was finally published in Pattern Recognition Journal on the such data irregularities, and this taxonomy distributes the data irregularities into 2 classes. One is called distribution-based irregularities, and the other one is called feature-based irregularities, of which we will look into the class imbalance scenario. Feature-based irregularities means some features may not be recorded for some cases. You try to handwritten digit recognition. You try to write a 3 or a 2, and some portion of your digit is just blank because the ink of your dot pen was not there. The ink didn't trickle down to those portions. So the pixels in those portions will not have the necessary color or the necessary features, okay, if you look into the image as a whole. So missing features versus absent features. Absent features means for all data items, all the features are not defined, okay? So that is feature-based. And in distribution-based, we have class imbalance. I will be talking about this part only. We have class Q, which means the class conditional distributions can be very disparate. And we have small disjunct scenario where the sub-concepts within each class are not represented properly. So that sometimes that is viewed as a subset inside class imbalance. So we will be talking about this. And when such irregularities are present, all the machine learning systems look like these 2 confused cats. Okay, that is the tragedy about it. And so before I go into this slide, let me talk about what is class imbalance. Okay, class imbalance is a scenario where inside the training set, one or more classes have very few representative samples. So the training, what is a training set? It's a small part of the entire data world, a very small collection of data items, which are manually labeled by some human expert into the all possible classes. Okay, like the doctor is labeling cancerous or benign. But if it so happens that in your training set, there are 96 samples from the benign class, and only 4, usually it so happens in case of rare disease detection, the disease class always have very few representative samples compared to the healthy class. So maybe you have collected 100 breast tissue mammograms, out of which 96, and when you are collecting it, you don't know which mammogram is belonging to which class, and the doctor is labeling it. So when the doctor is labeling it, he finds only 4 belong to the cancerous class, indicating onset of breast cancer, and 96 belong to the healthy, benign class. So your training set, training data will be heavily imbalanced. And when it becomes heavily imbalanced, usually the classification boundary can shift a lot. That is shown in this picture. The classification boundary can shift a lot and give you considerable deviation from the ideal classification boundary, which in terms of learning theory is called the Bayesian decision boundary, minimum risk Bayesian. And we can considerably deviate from there. That's the problem. The class in which we have Very few training examples is called a minority class. And minority class is the most important class. Now think of it, those who already have used, those of you who are experts or who have already used machine learning systems, think of the situation. 96 versus 4. 96 in benign category, 4 in onset of breast cancer or initially malignant category. Now think of this situation. You have a machine learning system for initial diagnosis of patients who come to an extremely crowded outpatient department of a government hospital, where we require such systems very heavily. It's not possible for a doctor to scan all the 4,000, 5,000 people coming every day. So, but this machine learning system is misclassifying all the cancer people. This machine learning system, out of 100, it is saying, it is misclassifying the 4-5 malignant cases every time. Actually, the system has become biased towards the majority class, and it is saying all the examples are the benign. Everyone is in good health. Everyone can go back home. What would be, from a machine learning theoretical point of view, we will say its accuracy is 96%. But what is its practical use? Zero, actually negative. It's a very negative thing, because it is missing the target minority class. This machine learning system should behave like an alarming system, and it should sound alarms to the 4-5 people who are at major risk. But even if it is missing all those people, from this theoretical point of view, its accuracy is 96%. This is the problem. In fact, few years back, 2 years back to be precise, we were doing a project with the National Payment Corporation of India. I don't know whether you have heard this name or not. NPCI is in fact a consortium of banks, okay? Government organization. They have a head office in Hyderabad. And our job was to detect the fraudulent transactions. NPCI have certain servers. In 2018, I came to know that whenever we buy something online by paying through credit card or debit card from Amazon or Flipkart or something like that, a copy of that transaction is actually stored in the NPCI server. Okay? So if I gift some item to my wife, they got to know what I am gifting, how much money I just spent, etc., etc. I didn't know that. Anyway, so all such transactions are specified by 62, features, or 62, and they have numerical, non-numerical, categorical, all sort of features together. Every financial year, Indian banking sector suffers huge loss because of fraudulent transaction. Somebody hacked your credit card number and other CVC and other credentials, and that person just did a purchase of 45,000 rupees. If you can prove that this is a fraudulent transaction, the bank has to, compensate you. That's why the NPCI wanted a team from ISI to intervene and, find out with some machine learning techniques to distinguish between fraudulent and genuine transactions. And we, at that time, faced a tremendous challenge while trying to apply all these theoretically very sound machine learning algorithms, which have been published in very highly cited papers and so on. We saw that in every week, the NPCI servers record almost 2.5 crore transactions. 2.5 crore transactions. And out of the 2.5 crore transactions, hardly 10,000 transactions are fraudulent. Hardly. The rest of it is genuine. This is a perfect example of highly imbalanced data. Do you understand? 2.5 crore versus 10,000. So the minority class is so few in number. 10,000 is very, very less compared to 2.5 crore. So under that situation, most of the algorithms actually fail. So this is one example from very practical life. And who fears whom? The classical machine learning paradigm comprising of neural networks, which are very sensitive to class imbalance, small disjuncts, absent and missing features. K nearest neighbors are also sensitive to class imbalance. If you look into this, you will see that support vector machine type classifiers are relatively less sensitive to class imbalance, but all other neural networks, K nearest neighbor, Bayesian inference, decision trees, and therefore random forest, okay, bagging, boosting type algorithms, all of them suffer from class imbalance, although they are kind of immune to other data irregularities. For example, decision tree is inherently immune to feature missingness. Even if some features are missed, decision trees do not require all the features to build up the tree. Therefore, they are kind of immune to such feature missingness, but all of them suffer from class imbalance. Okay? The fraud detection process, as I just said, we have to, this is a very high level description of what I already said. And we saw that the ML-based fraud detection has certain advantages if we artificially prepare some data or some data scenario where the minority class is not so small. This is very interesting. If we make some artificial scenario where the minority class is not so small, the majority and the minority classes have comparable size, then actually the number of, inside your training set, the number of examples in the majority class divided by the number of examples in the minority class is called the imbalance ratio, or IR. If the IR is less than 2, then it's a good situation. They are more or less balanced. In case of 96 versus 4, the IR was quite high, 24, 96 divided by 4. So if the IR is so high, then the life becomes more miserable. Although machine learning systems offer certain very nice advantages over the rule-based fraud detection system. But as I said, no advantage comes free of cost. So I will skip some of these, I already told you. So the problem with class imbalance is that the standard learners are often biased towards the majority class. And this is because the classifier attempts to reduce the global quantities, such as the error rate, without considerably acknowledging the data distribution. And if the data distribution is biased, the decision boundaries will be always wrongly placed. That gives rise to misclassification, especially for points from the minority class. It's quite simple to understand. You see, in practical life, what happens? You have, a student has to sit for an exam tomorrow, 2 chapters, differentiation and permutation combination. The student practices 100 examples from the chapter of differentiations and only 3 examples from permutation combination. He doesn't like permutation combination. So in the next day in the exam hall, he will be very confident on differentiation questions. He can make the derivatives and write down the answers. But when it comes to permutation combination and an unseen question is before him, he starts shivering, developing cold sweat and other things because he's very disconfident. Same thing happens for class imbalance scenario in case of machine learning systems as well. And the relative, okay, I will discuss the relative versus absolute imbalance somewhat later. Let us go to the first remedy to this, the popular handling techniques. One, there are 2 artificial data balance techniques. One is called oversampling, and these are very easy to understand. Oversampling means somehow you are making certain, reciprocations of the certain copies of the minority samples, and you are populating the minority class with more artificially prepared data items. Somehow you are interpolating between them, or somehow you are perturbing the minority class data items slightly to generate the near neighbors of those items. And in this way, suppose you had in original data set, you had only 10 from minority class and 90 from majority class. but artificially you generated 30 more in the minority class. So now you have total 40 versus 90, or maybe 50, 60 more in the minority class. This way, you are trying to rebalance the two classes in the training set. Okay. One such technique which still is very popular is called SMOT, or synthetic minority oversampling technique, from 2002. However, the oversampling technique increases the training complexity, leads to overgeneralization of the minority class, and can be very problematic if the class distribution is highly skewed. Skewed means even if the class comes from Gaussian distribution, the Gaussian covariance matrix is highly ill-conditioned. Okay, the difference between the eigenvalues of that covariance matrix is very high. There are mathematical characterizations, of course. Then the other technique is called undersampling, and RUS is such a technique, very well-known technique. Undersampling is just the reverse. It means throw away some points from the majority class, try to downsize the majority class so that the minority and majority classes may become almost equal in size. Then I will take some examples of these most promising techniques before going into our own works. Then we have the cost-sensitive methods. Cost-sensitive methods try to make some internal change inside the algorithm. Like you have a support vector machine classifier and you just formulate the optimization problem of SVM in such a manner that misclassifying a minority class point from the training set will be very highly penalized. But misclassifying a majority class point will not be dealt that seriously. So it provides different weightages on misclassifying different, members from the minority class and from the majority class. That such changes inside the optimization problem underlying your machine learning algorithm are typical for cost-sensitive methods. Apart from that, we can have algorithm-level approaches like kernel modification in maximum margin classifier, rank metrics, and in multitask learning, active learning methods where you can have interaction with the users and so on. Most of the algorithm-level approaches are heuristic, suboptimal, and there exists no theoretical performance guarantee. We can sometimes merge the rebalancing techniques with the algorithm-level approaches as well. Yeah, we will discuss the regression case later on after I just finish with these things. So the random sampling method, the oversampling and undersampling I just explained to all of you. Just as you can see, you will increase the set of the minority class, or you will decrease the set of majority class. The state-of-the-art algorithm is called SMOT, and SMOT works through these few lines, which you can read from here. For each minority sample, what we do, suppose we have the minority class and we have plotted these points in some feature space. So for each minority class, we find its k nearest neighbors. We randomly select j of these neighbors, and we randomly generate synthetic samples along the lines joining the minority samples and its j selected neighbors. J, what percentage of nearest neighbors you will select, depends on what percentage of oversampling is good for your case. And that again depends on the distribution of your data and your application area. So there are a lot of few things that you need to, there are a lot of heuristic parameters that you need to set. So if we are using 5 nearest neighbors, if the amount of oversampling needed is 200%, only 2 neighbors from the 5 nearest neighbors are chosen. That means for each minority class point, we generate 2 extra synthetic samples. That makes it 3 times the original size. That means 200% oversampling. Okay. So let us just illustrate with a picture. This is a very simple algorithm, but quite effective. Suppose the green points are in the minority class and the red stars are in the majority class. And you choose one green point as your target point, select the nearest neighbor, select from among the nearest neighbors, one of the points, then generate one synthetic sample on the line joining the target minority point and its nearest neighbor. So this synthetic sample is the X new, which you can see here, and it is very simple. It's just a point on the line joining Xi and Xj. So how you generate such a line? It's simply a convex combination. Take an alpha between 0 and 1, then do 1 minus alpha times Xi plus alpha times Xj. That is your X new. Okay. So oversampling works in that way. You select a number of nearest neighbors, then you generate synthetic instance on the target point and some of its nearest neighbors, on the line joining the target point and some of its nearest neighbors. And I explained it. These are some examples. So this red points, this is from an actual data set. These red points are the minority points, and you can generate artificial samples like this. The artificial samples, more or less, they look like they are situated on in a straight line, straight linear manner on some lines, because indeed it is so. These are convex combinations between the target point and its nearest neighbors. So sometimes overgeneralization means this can happen that a minority sample is completely surrounded by majority samples or majority points all around. So in that case, if you try to generate a new green point very near to this green point, which is surrounded by the blue points, so that will typically misguide the classifier and the generalization performance will be lost. What is meant by generalization? Generalization means a classifier may give very good result on the training data. On the training data, it is giving zero training error. But then new data points are coming, which were not there in the training set. So new test points are coming. If the classifier's performance is very poor on the test points, then we say it is overfitting. Overfitting means its generalizability is very, very less. Generalization capability means learn from a small sample of training sets and then generalize what you have learned on large other data items outside the training set. So oversampling sometimes restricts such ability. Okay, it leads to overgeneralization, as I said. So Smoot's procedure is inherently dangerous since it blindly generalizes the minority area without regard to the majority class. This strategy is particularly problematic in the case of highly skewed class distribution, since in such cases, maybe the minority class is very sparse with respect to majority class. So there are a lot of lacks for such classical approaches. Sometimes we go for borderline smooth and generate, we do some heuristic modifications in the way the neighbors are chosen, and we try to see which nearest neighbors are in a danger zone. Which danger zone means which nearest neighbors are more embedded inside the regions occupied by the majority class points. Okay, so oversampling with borderline smooth is a generalization of the original smooth, where we try to, if our data distribution is like this, we try to generate the minority examples away from the central points or along the borders of the minority class periphery. Okay, but this is also problematic when the classes have huge overlap. So when the classes overlapping region between the two classes is the worst region. It's the worst nightmare for many classifiers, including support vector machines. Because in the overlapping region, there are points which share characteristics of both the classes. And they are very hard to actually classify in absence of the human given level. Okay. So simply there are also many other techniques, some of which I will skip. Undersampling means undersampling, it comes with removal of noise and borderline examples. Let E be the original training set, and E dash contains all the positive examples and one randomly. So positive means majority class and one randomly selected negative example. So we can classify E with a 1NN rule using the examples in E prime, and all the misclassified examples from E, we can move to E prime. That means we can move all those examples which are misclassified by a 1NN rule, that means which are there in the majority class, but in a twilight region, in the region of overlap between the majority and minority, and which run the risk of being misclassified, those points are converted into minority class examples. This way, the minority class size is actually increased. Okay, minority class size is actually increased, and the majority class size is decreased. This is another way of rebalancing. So undersampling can be also done in many different ways. So these are the artificial data balancing examples. In one way, we can also the random undersampling randomly select some members of the majority class and simply deletes them. So we can have random undersampling versus oversampling. In oversampling, we repopulate the minority class. In undersampling, we prune the majority class. You know, these are very simple things to understand. Then there comes the cost-sensitive learning. This is what I am trying to say. The cost modification, this is somewhat more elegant, and it's an algorithm level technique. It is not the data level technique. Data level technique means you are rebalancing the data sets without changing anything inside the algorithm. In cost-sensitive learning, the cost modification consists of weighting the errors made on examples of the minority class higher than those made on. So when you misclassify a minority example, you will have high penalty in terms of highly weighted errors. If you misclassify a majority example, that is not so severe. You will not have that much high weightage for that. This is cost-sensitive learning, and somehow this weighting concept is incorporated in different algorithms in different ways. Okay, so you can create a cost matrix which can input the penalty of misclassifying the samples, and then while computing the total loss on the training set, you can aggregate the points from these misclassified samples together inside the cost matrix. There are a lot of things which could be done. I will show a very simple example of cost. I'm not going into cost-sensitive neural networks and other, sophisticated architectures right now. I will show a very simple example of k-nearest neighbor classifier and cost-sensitive learning. So what happens if I want to modify a k-nearest neighbor classifier for the class imbalance scenario? What is a k-nearest neighbor classifier? It's the simplest classifier proposed in 1958 actually, and still under active research. Let me tell you, the k-nearest neighbor philosophy is inevitable, whatever progress we may make. And it is a very simple algorithm. The very basic philosophy of k-nearest neighbor is a person is identified by the company that the person keeps. If your friends are all very sober, gentle, good, then you are very sober and good person. But if your friends are kind of goons or wagon breakers, then your character is at stake. So same thing happens here. You have a training data set and two classes, blue class and red class. Then a new query point or test point comes. You select you measure its distance, that means dissimilarity, with all the other training point members. And then you select the three nearest neighbors, the three neighbors or the 4 or 5 neighbors, k members of the training set, which are most similar to this query point. Then you see, so these are like your nearest friends, your friend circle. Then you see to which class these selected nearest neighbors belong. If they all belong to the blue class, then this point also belongs to the blue class. If they all belong to the red class, like the second picture, then this point also belongs to the red class. But if 2 of them belong to the blue class and 1 belong to the red class, then we will select the blue class as its class. So what we are looking at is the majority of nearest neighbors belong to which class. That class is the class of the new query point. This is k nearest neighbor. All of us know that. Now, we presented a very simple algorithm for adopting k nearest neighbors for the global imbalance handling scheme. This is a very simple thing. Obviously, this paper where it was published, there were many other mathematics and other things which I will for now avoid, but you can go through the paper itself. We used a very simple cost-sensitive imbalance handling scheme, global imbalance handling scheme, or GIHS. What is our method? If there are C classes, suppose we have 3 classes in the data set. So the ideal probability of appearance of each class is small r, which is 1 by C. It's like you have a box. Maybe there are 4 points from one class and 6 points from the other class. It's like there are 4 blue balls and 6 red balls in your box. So if you close your eyes and pick up 1 ball from the box, what is the probability that it belongs to the blue class? Obviously 4 by 10, red class, 6 by 10, same thing here. So the ideal, this is ideal probability. So the ideal probability of a point to belong to one class is 1 upon C. Sorry, I just told you the original probability, my example. Ideal probability is if you have 2 classes, then the probability of coming from any one class is half, ideally. But since you have 4 points in one class and 6 points in the other class, the actual probability would be like this, the example of drawing the ball from the box. And that will be 4 by 10 and 6 by 10. So you see the original probability, which is NC by N. NC is the number of points in the small cth class, and N is the number of points in the entire training set. So we calculate the weights WC in this way, R by PC. That is the ideal probability divided by the original probability. So each class has the class-specific weight WC as R by PC. This is a technique which gives higher weights to minority classes while lowering that for the majority classes. Let's see how it works with a simple example. It's very simple. It requires linear time to calculate the weights and so on. Just let us see this example. There are 20 points in the training set. Out of the 20 points, 4 blue points belong to one class and 16 these dark red points belong to the other class. So what is the imbalance ratio? 16 by 4. 16 is the majority class size, 4 is the minority class size. The imbalance ratio is 16 by 4. Okay. Now a new point comes. Now our R, the ideal probability, which is 1 by C, and C is 2 here. So R is 0.5 and 0.5. P, what is P? P is the original probability for each class, P1 and P2. Number of points in that class by total number of points. So what is P here? There are, for the blue class, it is 4 by 20. 4 by 20 means 1 by 5, that is 0.5. And for the red class, it is 16 by 20, which is 0.8. So what are our weights for the classes? The blue class has the weight of 0.5 by 0.2, which is 2.5. And the red class has a weight of 0.5 by 0.625, which is actually, 0.5 by 0.8, which is actually 0.625. So now you see, when we have among our 3 nearest neighbors, when we have all neighbors in the red class and no neighbors in the blue class, the counts are 0 and 3. These counts will now be multiplied by these weights. Previously, we were only looking at how many members belong to which class. Now we are looking at how many weighted count of nearest neighbors belong to each class. Weighted count, not the normal count. So when this situation happens, that you have 1 point, so this, you see the position of this diamond, this query point in our middle picture. So in this situation happens that this diamond has only 1 neighbor from the blue class and 2 neighbors from the red class. The counts, normal counts are 1 and 2, but the modified counts are 2.5 and 1.25. So if we look into these weighted counts, our inference is this diamond belongs to the blue class. If you run a normal KNN, the normal KNN will put this diamond in the red class. But there is a high chance that the diamond actually belongs to the blue class, which will be done by this weighted KNN. Okay, just as an example. So this was one of the very simple works, and we were comparing with many other techniques, including KNN plus MOTE, KNN plus RAS, then KNN, CCND, WKNN. There are various types of other algorithmic variants of different techniques for handling the imbalance. And we were measuring our, performance of the algorithms on the basis of GM, the G-mean measure. The G-mean measure is actually the square root of TPR, true positive rate, versus into true negative rate. It's a geometric mean of these two. Actually, GM in comparison to accuracy is not at all a good measure in case of class imbalance handling data sets. G-means is a much better measure. If all the the examples are classified as positive or majority class, then the TNR would be 0. If TNR is 0, TPR is 1, even then G-means would be 0. That's why G-means is a very important metric for handling class imbalance. So in the deep learning era even, we have deep learning methods are very much applicable to image classification, medical imaging, and diagnosis of rare diseases. Also, in among the serious applications, there are weather prediction, cyclone prediction, okay, geostorm type of calamities if they come. But such rare events always have very few samples compared to the regular sky, regular satellite pictures, which are much huge in number. So imbalance continues to affect the deep learning neural networks. Rest of the talk, we are almost at the last part. Rest of the talk will be dedicated towards deep learning based class imbalance handling. And you can see the SUN 397 dataset. There are 397 classes of different images under this dataset. This is one of the benchmark datasets for testing deep neural networks on imbalanced scenarios. And it has a long tail distribution. Long tail distribution means some of the classes appear very few times in the datasets. There are very few members in these classes. There are huge number of members in some of the classes like drawing room, as you can see here. Along y-axis, we are measuring how many members are there in these classes. That is the number of occurrences of the class. And along the long tail, we are saying there are also some images some classes which have very few samples inside, like the public library. Public library image is not that popular. People prefer to see lots of good drawing room images. Library, how many of us go to library to read a book nowadays when we have WhatsApp University with us? So, of course, the long tail distribution has the minority classes on that. And there are various techniques people started to adopt in the deep learning era. Currently, it is gaining huge attention. For example, if we look at the CVPR 2016 paper, this was one of the first works for learning deep representation on imbalance classification, published in CVPR, one of the two highest grade conferences in computer vision. So they say that most instances from the minority class come with high degree of visual variability. So this method learns, basically adopts the CNN embedding. CNN embedding means the way CNN summarizes each image into a small, small dimensional vector with abstract and high-level features. They use a new quantuplet sampling scheme, and then the CNN learning was done by a triple header hinge loss, which is an example of the cost-sensitive learning, where the majority and minority classes were unequally, penalized in the training set loss, and thereafter they optimized it by gradient descent. Wang et al. In the famous NIPS 2017 conference, they came up with the learning to model the tail, and they proposed a meta network based on deep residual learning model to transfer the meta knowledge learned from the head to the tail of the class distribution. And this type of methods are also there. I'm not going to read it out because we don't have enough time. I will show one of our very recent and very popular approaches this time. So traditional oversampling As I just said about SMOT, characteristics of SMOT is it is less likely to overfit compared to the naive resampling. There is no loss of information. Undersampling, when we just throw out some examples from the majority class, we may miss very important information about certain portions of our data universe. That is called loss of information. SMOT doesn't run the risk of having loss of information. But SMOT still requires tuning of additional hyperparameters. How many number of neighbors? What % of nearest neighbors will be considered? What would be that alpha value based on which we are generating the point on the line joining the target and the nearest neighbor? So there are these hyperparameters which you need to tune. For proper choice of such hyperparameters, the generated samples will obviously follow the distribution of the real minority class. So if this is a convolutional system, what does a convolutional layer neural network do? It takes images as input. Then through convolution max pool layers, repetition of convolution max pool ReLU activation, these layers, it finally generates a vector comprising of, the vector is much small dimension, much less dimensional than the whole image. And the vector summarizes the most important abstract and high-level features of the image numerically. That is the biggest point of convolutional layers, okay? Selling point of convolutional net. So we can do, after the convolutional layers, generate a concise representation of the images provided at the input. We can do the SMOT in that latent space learned by the convolutional layers, okay? SMOT means we can generate additional, latent space points, each of which should ideally represent an image in the full scale space. Then the classifier, which are formed with the final layers of a CNN architecture, this final layer classifier can work on the rebalanced dataset in the latent space, not in the original image space. This was the idea of the 2017 paper on deep oversampling, which appeared in CVPR. And then there comes our work in 2009. This paper was published in the ICCV 2019. This is the other very high-end computer vision conference, IEEE ICCV 2019. And we call it GAMO. It is called Generative Adversarial Minority Oversampling. So for the rest of the talk, I will try to give you a very concept level description of GAMO before I conclude. Concept level because we really don't have enough time, but I will make these slides available, try to make them available. See, in deep learning, we have two types of generative inference models. One is called, there are two types of deep inference models. One is called the predictive learning, where the classifier is happy to learn just a decision boundary between the classes. And the other one is called a generative deep inference model, where classification comes secondary. The generative deep inference models try to learn the underlying probability distribution of the training data from different classes. They try to model, estimate, or learn that distribution. Very interesting. So you see, predictive models are also called discriminative models, like support vector machines, linear regressors, or convolutional nets. They learn a decision boundary between the two training points, between the two classes or more classes. On the other hand, the generative model tries to learn the probability distribution of the data. This is an age-old problem in statistics. For statisticians, it's a 150-year-old problem. What is this problem? I give you 10 numbers, 1.3, 2.8, 6.7, minus 9.8, and so on. And I ask you, give me the Gaussian distribution from which these 10 numbers are most likely to be sampled. You will easily do the MLE, or maximum likelihood estimation, or you will do MAP, maximum a posteriori estimation. You can do Parsen window based kernel density estimation. You can do a lot of stuff and give me an estimation of the underlying Gaussian from where these points have been sampled. But if I give you, instead of 10 scalar numbers, if I give you 500 images, and each image is having 100 cross 100 pixels, 10,000 pixels in each image, all statistical methods will fail. No way to estimate such high dimensional objects, no way to estimate the underlying probability distribution from where such high dimensional objects have been sampled. It's still a very big challenge to estimate these things in a mathematically guaranteed way. See, for a normal person like us, you, me, everything comes from nature or everything comes from God. To a statistician, everything is sampled from an underlying stochastic process, which is governed by certain probabilistic parameters. If you get hold of that probability rules from which these samples have been generated, then you become like God. You can sample from the estimated distribution and generate artificial objects which will look very realistic. That is where GAN is coming in, or VAE is coming in. The deep generative models try to estimate the high dimensional underlying probability distribution by using neural networks. Two such deep generative models are now creating wonders. One is called variational autoencoders, or VAEs, and the other one is even more popular, that is called generative adversarial networks, or GANs. Okay, so I will skip through most of these things. I just told you what happens inside the convolutional neural network. This will be important. So in the convolutional neural network, you give a picture. The picture is converted into a vector of abstract and high-level features, a vector of real numbers. These real numbers will summarize the most abstract and high-level features inside the picture. And these features are most contextual for the current classification problem. Which features are most contextual? That will also be learned from a single cost function at the final output. Because when you are trying to demarcate between birds versus non-birds, everything else can be neglected apart from the presence of a beak, presence of feathers, colored feathers. These two are the most important abstract and high-level features. Convolutional neural network try to summarize the image in that way. And finally, after all these features are learned, the classification is done. So before going into the classifier, if I reverse the flow of the convolutional neural network, so ConvNet converts an image into a vector. If I reverse the flow, I can give a vector and I can generate an image. Okay, so the input is a vector and the output is an image. That is called deconvolutional neural network. Thereafter comes GAN. GAN, you see, the paper was published in 2014, and till date it has 30,000 citations. 30,000 citations. It's so well used and so new. After GAN was trained with medieval period portrait artist drawn pictures, GAN generated its own portrait, generative adversarial network. It generated its own picture, which looks like a charcoal drawing on a canvas by a famous medieval period artist. And there is a short signature where at the bottom corner of the picture where the artist should sign, there is a signature. This signature is basically the objective function of GAN. So this picture was auctioned in USA for US $432,500. That's the news. Anyway, I will skip most of it. What GAN does is very simple. Before I go into my work, I need to tell you, GAN has two systems. One is the two neural networks. One is a generator neural network and one is a discriminator neural network. These two the generator neural network has an image, has some vectors at its input, and starting from the vector, it generates the images. Okay, it is like a deconvolutional neural network. So the generator network generates lots of images. Discriminator neural network is like a two-class classifier. It can be a logistic regressor as well. This network has access to the external training set. So it knows how original realistic images look like. So the generator tries to fool the discriminator by presenting at the input of the discriminator its own generated fake images. The discriminator tries to catch up the generator by assigning a very low score to those images and thereby classifying them as the fake images. Based on the criticism of the generator, of the discriminator, the generator improves itself. Based on the more access to training images, the discriminator also gradually learns how to finely demarcate between the real and fake images. And these two neural networks are playing a tug of war with each other. They are in competition. All competitions are not harmful. Through this competition, both of them improve. In game theoretic perspective, we say these two neural networks are playing a two-player zero-sum game with each other. Okay, through which both of their capabilities improve. And when GAN training is successfully accomplished, for GAN, classification is not the real business. The real business is generation of almost realistic artificial images. So we thought, since GAN can generate images from a specific distribution which should look very realistic, why not use it for generating artificial samples inside the minority class to populate the minority class in some way? So the adversarial oversampling works like in which way? We first started with generator plus classifier. We thought we will not have a discriminator initially. We will have a simple classifier network and let the generator generate more points at the fringe of the two classes, at the portions where the two classes overlap. But this method had so the generator should generate such training points which will fool this classifier. That way, the generator will be able to generate more critical points at the overlap between the two classes or more classes. This was one of the ways, but then some of these points started to go outside the periphery of the feasible region in the latent space. And as a result of that, those images started to look like ghost images. So we modified the generator and came up with a convex generator. Convex generators try to generate convex combinations of the existing minority points. They take a convex combination and ultimately they perturb that combination to generate new points within the convex hull of the minority points. So generated points are now constrained to be inside the convex hull of the minority distribution. Then finally we added another discriminator, and we changed the GAN's architecture. GAN is a 2 neural network architecture. We changed it into a 3 neural network architecture and came up with GAMO. So in this slide, I will explain what exactly happens inside GAMO, and then I will just simply conclude because the time is almost up. So this is what happens in an unaided classifier. Unaided means it's a simple classifier. No auxiliary mechanism has been given for imbalance handling. You can see the blue class is the majority class, thickly dense class of points. And the red class is just containing some sparsely packed points, which are minority class. If we use an unaided classifier, this is the best decision boundary it can learn. This was from a multi-layer perceptron. And this decision boundary, you can see it has misclassified lot of red points. This misclassification is not very good. It is telling a person that you don't have any symbol of carcinoma, although the person may be developing cancer inside his body or her body. So that is very dangerous. This varies from context to context. A patient who doesn't have COVID, if you say, yes, you have COVID, the patient will start, taking immunoboosters, tea, vapor, zinc tablets, which are not that harmful. But if you just change the context, say somebody that you are not having cancer, although the person is having cancer, the person will deteriorate his health or her health very quickly, and that could be fatal for him or her. The reverse is also true. Somebody doesn't have malignancy or cancer and you say, yes, you have cancer. You must start chemotherapy right now. And the person's good health will be ruined. So vary the perspective, majority minority misclassification will become different, differently serious. Now, when we prepare a convex generator and a classifier, the convex generator generates these green points within the brink of the minority class. And now these green points, you can see lots of green plus points here, which are generated because of the convex generator aided with a classifier. It's a twisted GAN architecture for imbalance handling. But here also, we see lots of majority points are misclassified. Majority points misclassified means you are asking a healthy person, you are telling a healthy person that you have cancer. It's as serious as that. So majority misclassification, you can see a lot of majority points have been misclassified. This yellow region is the minority region learned finally. And the blue points are within that. GAMO adds an additional discriminator into the architecture. This discriminator actually uniformly spreads the green points within the non-convex. Here, in this case, it's a non-convex distribution, which is the most general one. So the green points are uniformly distributed within the space of the minority class. And that kind of motivates the classifier to learn the proper decision boundary in case of deep imbalance data sets. This is exactly what GAMO does. So we added a new, discriminator into the architecture. This is a probability distribution convergence diagram, which shows how the three neural networks learn different distributions. The whole architecture is summarized here, which is there in our paper. Also, you type the name of the paper, it will lead you to the GitHub page where you have the complete Python code and implementation of the paper. We created a 3-player game. So this original GAN is a 2-player game between two neural architectures, and GAMO is a 3-player game. We showed in the paper how this 3-player game is actually minimizing the divergence measure between the distributions, probability distributions of the original minority class and the generated minority class points. So I will have to go to conclusion part before I make any other comment. So GAMO is a very effective oversampling technique for end-to-end system. It scales very well with large classes and many minority classes. It improves the quality of the images generated. Actual images can be seen through GAMO, you can see. And it doesn't have mode collapse problem. Mode collapse means the original GAN suffers from high degree of mode collapse where, same image can be generated again and again. So if the generator can fool the discriminator with a particular image, it will continue to do so. So this is, you can see that similar image has been generated multiple times, but these are the images generated by GAMO. And you can see these are the artificial images, not in the actual minority class, from different classes. These are the celebrity images, and you can see different faces every time. So miles to go before we sleep. The class imbalance problem is actually, there are a lot of things to be done ahead. Theoretical analysis and insight, standardized and uniform benchmarking of different class imbalance data. We are having a project under DST for the COVID-19 detection and other COVID-19 versus bacterial pneumonia versus viral pneumonia, other viral type pneumonia, and benign lungs images. So such medical diagnostic systems suffer from huge degree of imbalance, but there is no publicly available, well-documented benchmarking of such data sets. Standardized and appropriate performance metrics should be devised. Then the major problem of this time, which is semi-supervised learning. Semi-supervised learning is a very big problem where we have few shot and zero shot learning paradigms. And we say, okay, For a human being, for a human kid, you show that kid only one picture of a giraffe. The kid goes to zoo with you and looking at the giraffe, it says, Papa, look, that's a giraffe. But for a neural network, you have to show it 100 giraffe pictures. Why? Training data is very costly. I told you, you hire a doctor and have him mark 100 images, you need to pay him 2,500 US dollar if he is really an expert doctor. So training data is very costly. Data is cheap and abundant around us, so much data around us. But training data means labeled data, already classified data. That is very costly. Semi-supervised algorithms try to reduce the need of training data for deep learning situations, and class imbalance can be a major obstacle behind development of such algorithms. I will skip most of these things. So that's it. There is a lot of things to be done with class imbalance. I would like to stop here because I don't want to stretch it beyond the time. Finally, thank you very much for your patience. Stay safe and stay protected in these dark times. If you have any questions, maybe we can take a few questions now.
Yeah, thank you very much, Dr. Das. I think it's a great presentation. I think the information is a wonderful information given to us. One of the best sessions we have attended. So thank you very much, Dr. Das. And there are one question which is posted here from the participant. How to handle imbalanced data set for a regression problem where a target variable is continuous and highly skewed?
Yeah, first of all, this skewed situation is a very different situation. We assume that the classes are having very different shapes of distributions inside. One option is through model processing. Model processing is one of the strategies for handling imbalanced data, which is used in context to regression, especially, and you have the UBR, the utility-based regression system. One of the rare techniques that works very efficiently with imbalanced or non-uniform data. The basic idea of UBR is obviously to add a cost penalty for the wrong estimate, which varies based on the relevance function. So if you have very few variables, so you have different variables, and these different variables can make different predictions on your regression task. In case the relevance function is close to 1, which means a very rare observation highly contributing to the imbalance or skewness of the data, in that case, the cost penalty should increase and may reach the maximum. So the relevance function under UBR may be defined in various ways. One way is to make it inversely proportional to the probability density function itself. So utility-based regression or UBR process, you can look into it. Also, there are some boosting regressors like the XG boost, extreme gradient boosting regression. And because boosting, it also, the points you get for as your training points for regression, boosting provides different weightage to these training points. Usually under regression, when you have skewed distribution, the best thing is to use such internal penalties inside your regression algorithm. If you drop me a line of mail, I can send you some detailed papers where you will find these detail of these techniques, and then you can discuss. Okay.
Yeah, thank you. Thank you very much for answering the question. I think I request all the participants, if you have any queries, please post it in the chat box. Maybe we'll get back to you as early as possible. Thank you, Dr. Das, once again, delivering such a wonderful expert talk today. As a token of appreciation for delivering such a wonderful talk today, you are honored with a beautiful tree.
Great.
Because you all talk about greenery and sapling of trees and everything.
Very nice.
We thought we can honor with a beautiful tree. So I'll send you the will send you the this certificate to you by email very shortly. Okay.
Okay.
So yeah. Thank you very much once again. And I would like to thank all the participants be a part of this such a wonderful talk. And all the executive committee members be a part of it. And if you have any queries, please get back to us. Maybe you can put in the chat box. We'll get back to you as early as possible.
Maybe
Thank you very much.
I can share the slides to you. If you can, if
Yeah.
somebody wants, you can.
Yeah, please. I request to share the slides. I'll pass on to the participants, whoever is required.
Right.
The particular slide. Yeah, Vishwas, do you want to say anything? We'll conclude the session. Vishwas?
Yeah, so thank you, Professor Das, today. And we'll be in touch with you for future collaboration as well.
Sure.
Thank you, Ramakrishna, for hosting this evening.
Yeah, I think thank you very much. Thank you very much, everyone. This is the time to conclude the session. Thank you. Thank you.
Thank you.
Thank you.